So first of all, are there any questions about the first lecture? Okay, so I mean, I met some of you, in the corridors, and there was a little bit of a confusion about what I was doing last time. Just to keep notations simple, I wrote this, that the magnetic moment is some vector s here. But typically one uses s to denote spin. So people were thinking that I'm just looking at the spin part of the angular momentum. But in general, I mean, the treatment that I worked out is valid for any s. I mean, as Mustansir was saying, I mean, s can arise from orbital part of the angular momentum, or you have L dot s interaction, then it could be a combination of both L and s and so on. What one needs to keep in mind is that this s is a quantum mechanical operator, but it can take only integer values or half integer values. So for if you just have only spin, then s equals to half. If you have L equals 1 angular momentum, then s is equal to 1. If you have a combination, then you can have some 5 halves or 3 halves or whatever. So whatever I did was valid in general, except that it was not just spin. It could be any source of magnetic moment. That could be orbital, spin, combination, whatever. So you can keep that in mind when you are going through the calculations that I did. I also worked out basically the case where one is ignoring spin-spin interactions. So one has only the interaction of magnetic moment, the external magnetic field. That was the case of paramagnet. And there, before actually doing the calculation, I sort of specifically said that this is for a system of spins or magnetic moments which are localized, in the sense that you have some ions sitting on a lattice in a solid, and they can have some magnetic moment. And then you apply a magnetic field, and then there is this interaction of the magnetic moment with the field comes into the picture. And one can have paramagnet if the interactions are small or negligible, or if one is at high temperature. This is actually important. You see that the scale here is quite low. So if one is at temperature, often the interaction between magnetic objects, magnetic moments, the energy scale with that can be quite small compared to the KBT temperature energy. And as a result, I mean, one ignoring the interaction is not such a bad approximation. So although interactions are always there, but depending on the material that you're looking at, and also what temperature you are interested in, one can make this non-interacting approximation, which gives reasonable results. And even in a ferromagnet or some other sort of more complicated kind of magnetic systems, if you go to high enough temperatures, typically one gets this Curie behavior, that susceptibility goes as 1 over temperature. At lower temperatures, when the KBT becomes comparable with the energy scale of these interactions, then you will see deviations. As Mustansir draw this picture where you have spin glasses where it goes as 1 over T, but then something else happens, and then there is deviation from that. So although it's a very, very simple calculation, the ideal paramagnet, so to speak, it's a good starting point, because it tells you about how one can use statistical mechanics to actually get the macroscopic susceptibility, and one gets also good agreement with experiments at high temperatures. So that's a nice thing. I also mentioned, and this I didn't have time to sort of elaborate upon, was that in the large S limit, one gets this Langevin function. So, and this Langevin function, I also mentioned that that is what you would get if you treat the spins classically. So how do you treat the spins classically? This is again a homework problem that you may want to work out. So you have this classical basically means that the spin doesn't have quantization or anything like that. It's just a vector of some length, S. And there is a magnetic field in some direction. So basically the interaction remains the same. The magnetic moment expression also remains the same, except that S, instead of treating it as a quantum mechanical object, we'll call that it's just a unit a vector of length S. So the energy will be again, you have this minus G times mu B times S, and then there will be some cosine theta. The energy of associated with this magnetic moment, treating this S as a classical vector, and then there is a magnetic field, so, and there is H. So this is the energy of this object. And of course, the energy will be minimum when this cosine theta is equal to 1, which basically means that the magnetic moment is aligned in the direction of the magnetic field. And as it goes anywhere else, then the energy will be higher. Now, given this, do you know how to actually calculate the susceptibility? There, I mean, earlier when we did this calculation, we sort of did a partition function. Partition function involved a sum over the discrete values that this Sz can have. So Sz can have minus S2 plus S, there are 2S plus 1 discrete values and so on. Now I am treating this as a vector, classical vector, which can make any angle of the magnetic field. So you know how to calculate, for example, the partition function of this? Partition function, if you want to calculate, then you have to look at basically e to the minus energy divided by kBt, right? So that will be G times mu B times S times H cosine theta. This is the Boltzmann factor, e to the minus energy divided by kBt. And then you have to sum over it. I mean, that's, I mean, when you do the partition function, you then basically do a, earlier we did a sum over all the possible states, but now we have to do an integral, because this theta can be anything. And the theta is actually an angle in a three-dimensional space. So when you do the integral, then what do you do? You will do d theta, but there is a phase space factor. What is that factor? When you do sort of using polar coordinates, when you do an integral over the angles, then what is the factor that you use? 2 pi sine theta d theta. I mean, if phi integration gives you 2 pi, and then there is a sine theta d theta part. So we will do it here, 2 pi. I already had integral there. So this is basically my Z1, the partition function for a single spin. And then as before, you basically, when you have n of these things, then you take Z1 raised to the power n and so on and so forth. Take the log of that multiplied by kBt to get the free energy, differentiate with respect to H to get the magnetization, etc., etc. So all of you know how to do that, right? So this is a simple exercise that is useful. And what you will find out is exactly what we got in the large S limit of the quantum calculation. Okay? So this is something that is an exercise that it's useful to actually do this, because later on when we talk about, let's say, Heisenberg model and things like that, in many situations we'll treat the spins as just classical unit vectors. We'll not really take into account the quantum nature of the spins. So how to deal with this is something that you should be sort of comfortable with. And the Langevin function I have written down. So I mean, this is a hyperbolic cotangent and L sub y, Langevin function of some variable y, hyperbolic cotangent of y. Sorry. So you will get that function in the expression for the magnetization, susceptibility, etc., etc. And you will also get 1 over T. That's a more general result. That's if you look at the susceptibility in this system, since again there are no interactions, susceptibility will go as 1 over temperature. Theory law will be valid. So this is all I want to say at this point about paramagnets, and I basically emphasize that you are dealing with localized spins. That is important because there are a couple of places. I mean, nobody objected, but you should have objected. When I wrote down the partition function for n particles, then I just wrote z1 raised to the power n. But even if you do it for ideal gases, you put in this factor of 1 over n factorial, right? Because they are, I mean, assuming that all the moments are the same. But it doesn't matter if the particles are localized, then whether they are identical, whatever, it doesn't matter because the statistics doesn't matter. Whether they spin a 5-half or spin a half or spin 1 doesn't matter. Whether they're fermions or bosons doesn't matter because their wave functions don't overlap. So this exchange that he was talking about, that integral is always 0, so it doesn't matter. So that's one thing. The other thing is that the energy I wrote only the spin part of the energy or the magnetic part of the energy. The interaction of the magnetic moment with the external magnetic field. And again, that's okay because, I mean, we are saying that this particles they are not moving around the system. So you can, didn't put in kinetic energy or potential energy, all those things we didn't put in. So it's a bit of an approximation because, I mean, as he was talking about, I mean, even there is a lot of physics in one of these ions. I mean, there are many electrons, and then, what kind of property that these ions will exhibit that one needs to actually work out, and particularly to find the value of S. Value of S is unclear. Value of G is not clear because G is equal to 1 for orbital momentum, G is equal to 2 for spin momentum. So if you have a combination of spin and orbital part, you get a J, then what kind of gyromagnetic ratio you'll get is not always clear. Okay. It's clear, but once you do the calculation to find out. So these are situations where the magnetic moments are all sitting at lattice sites, localized. But of course, I mean, you have a situation which is also quite familiar, where the magnetic moments are not localized. And that situation is realized in, let's say, in a metal. Metal, you have conduction electrons. They carry spin angular momentum, so they carry spin moment. They are moving around. And here, we cannot ignore the fact that the electrons are fermions. Right? This is again something that you know already. I mean, when you are just looking at electron gas problems, let's say at 0 temperature, simple case where the single electron wave functions are plane waves, then you say that all states with k less than the Fermi wave number are fully occupied. That's every state outside the Fermi sphere are fully vacant, and when you have finite temperature, that gets a little bit soft at the edges. But this is very important because here the results that you get even for just the electron gas is so very different from what you get from an ideal gas of classical ideal gas. In the sense that all the thermodynamic properties are very different. So the point is even simple ideal gas treatment will be very different depending on whether we are talking about a classical ideal gas or a fermion or boson or something like that. So the next thing that I want to do is do again a calculation of paramagnetism, but now I will, instead of looking at localized magnetic moments, I will look at the electron gas, where now Fermi statistics will come into the picture, and of the magnetic moment of the electrons that will now give you some magnetic behavior. So we will see paramagnetism because again, the point is, if you have this S equal to half, doesn't matter. If you have electrons, this S will be equal to half. G is equal to 2. So again, the state when the magnetic moment is parallel to the field will still have lower energy. So there will be more occupation, and there will be a magnetization as long as there is external field. But you'll see that the dependence of that magnetization on temperature and things like that will be very different from what we got for this calculation. Because the fact that now we are looking at a system of electrons and they are not localized, they are mobile, and as a result, one has to worry about filling of the Fermi surface and things like that. So we have just seen ideal paramagnet, but now what we are going to do is name that is given in the literature is Pauli paramagnetism. So we are looking at a bunch of electrons, free electrons. I mean, just conduction electrons in a metal, will approximate them as free electrons. The single electron wave functions are still plane waves. So we'll just have the ground state is where all the plane wave states with k less than the Fermi wave number are fully occupied. As I said, the excited state will be where you take some from below the Fermi surface and put it above the Fermi surface. So here, let me just do. Now, I will write E up. Up basically means Sz plus a half. I'll denote it by up. And Sz equals minus a half, I'll denote it by down. So if Sz equals plus a half, the energy, and now we have a k vector that specifies the single particle state. This will be basically, let's call it E0 of k. E0 basically means when there is no magnetic field, and then there will be that contribution of the energy. So Sz will be, so mu is in the, again you have minus mu dot h thing. So there will be minus g times mu v is equal to 2 here, Sz is equal to half. So the energy will be reduced to mu v times h. And the other case, I mean, you have down of k will be E0 of k plus. And you can say that, I mean, E0 I'm writing, but E0 plane waves, E0 of k will be h bar squared, k squared. If there are actually free electrons, then we put in the free electron mass there. But in physical systems, this electron reside in a solid. So if I look at even conduction electron is solid, the mass is not exactly the same thing as the free electron mass. There will be some effective mass coming from band structure effects and stuff like that. So in general, I will don't bother about it. I'll call it some m. Effective mass of an electron gas that we are interested in. So this is simple. This is just making use of the fact that the energy is modified through the interaction of the magnetic moment with magnetic field. Now, given this, if I want to find out, for example, how many electrons are up and how many electrons are down, how would you do that? Let's say now I have this system at T, and I want to find out. Now you see the energies of the up and down electrons are different. So the number of electrons that will be in the up state and number of electrons that will be in the down state, they will not be the same. Right? So basically, you do the same thing as you do when there is no magnetic field. What do you do when there is no magnetic field? You say that just energy is only E0 of k. From there you get a density of states, and you say that the density of states T equals 0, fill the density of states up to the point so that all the electrons are accommodated. You say that Pauli principle says that single particle state we can put only 2 electrons, one up and one down. Here the energies of the up and down electrons are different, so you have to do this calculation separately for up electrons and down electrons. Okay. So you have to then put in the Fermi distribution. This tells us the average occupation of a particular single particle state of energy E. The new thing that comes in here is basically this thing called the mu. What is mu? Chemical potential, right? At T equals 0, it is the Fermi energy, but at finite temperature, there is some action. So this mu has to be chosen in such a way that the total number of electrons that you have actually matches the number of electrons that you have in the system. So this is grand canonical ensemble where you fix mu and then from that calculate the number of electrons and that determine mu by demanding that the number that you have calculated should match the actual number of electrons that you have in your system. So it is the same thing. But this energy now has two different values. Depending on whether you look with upspin or downspin. So it is quite simple. One more thing that we want to decide, write down is the density of states, which we'll call rho 0 of epsilon. This density of states is defined for the original problem without the magnetic field. This energy spectrum is given by this epsilon 0. Doesn't have to be exactly this, whatever it is. If you have a solid, then there is a band structure effects and so on and so forth. But from that, you can calculate a density of states. Normally, when you do density of states, then you also sum over sigma. The spin is state you put 2 electrons. But here, we cannot treat up and down electrons at the same footing. So this is basically a density of states, but for only one kind of spins. Okay? So from then, given 2, it's just write down n up rho 0 of epsilon, the Fermi factor, exponential minus epsilon, and the energy now becomes epsilon 0 minus, or the epsilon 0 effect is taken into account in this rho 0. So, I mean, it will be epsilon plus minus mu BH minus mu energy is minus mu BH for electrons. So I'm putting in this epsilon minus mu BH, and this minus mu over kBT is whatever you have here. And n down will be with a plus factor here. So let me write them down also, just for the sake of completeness. Exponential minus epsilon plus so this tells me about how many electrons are above with spin up and how many electrons are spin down. And these two are different because here, well, this comes with a minus sign and this comes with a plus sign. And of course, I mean, what is mu? That is something that you determine. Total number of electrons is n up plus n down, and that has to be equal to the actual number of electrons that you have put in your system. So that will determine what the value of mu is as a function of h and t. So it's not a trivial calculation, because the form of this Fermi function is somewhat complicated. So we'll be looking at basically a limit where one can get away with not doing much calculation, and that is the limit where I will say that this kBT temperature is very small. This temperature is very small when the form of this function is such that if the argument here is negative, then it goes to 0. Argument there is positive, it goes to 1. If epsilon is bigger than this quantity, then you will have negative, and then there is a divide by kBT, so it's negative infinity to 0. Smaller than that quantity, then you get something which is like 1. It is like saying that the Fermi function has 1 and continuous to 0. That's the Fermi energy. So we are making the assumption, but one can do much better. One can basically look at the effects of temperature, how this thing actually is not exactly a step function. It gets smoothened and so on and so forth. But just to see what happens, I will approximate this quantity, integral rho 0 of epsilon, and I will say that epsilon has to be less than this quantity. So, I mean, epsilon has to be basically less than this mu h plus mu. You see that epsilon minus mu h minus mu is there. So, epsilon has to be bigger than, if it's bigger than, then you get 0 basically. And similarly, here we will approximate it to 0, but it is mu minus mu b h rho 0 of epsilon d epsilon. And you can see that this values, because one is going all up to mu plus mu b h, the other is going to mu minus mu b h. H equals 0, then you will get the same value for both cases. Will be any magnetization, because magnetization is basically the difference between n up and n down. So now this becomes simple. You say that, again say that mu b h, we are looking at the h going to 0 limit, you are looking at the 0 field susceptibility and so on. So this is just the difference between these two is an integral of this rho 0 going from minus mu b h to plus mu b h. So basically one can just write down what the magnetization is going to be. M is going to be basically M is G is equal to 2 and mu b, and S equals half that we have already looked at. So it's basically mu b square-wave derivative, because for the up spins I am going all the way up to mu b chemical potential plus mu b h. For the down spins I am going to chemical potential minus mu b h. Chemical potential has to be the same both up and down electrons because they are coexisting. So the number of down electrons is going to be smaller than the number of up electrons, and the difference is basically going from this limit to that limit. And if this mu b h is small, then this difference is, I assume that this rho 0 evaluated at mu multiplied by twice that much. So and then 2 b h and this rho mu. So this looks correct. So then I look at the susceptibility, the derivative of this M with respect to H. So M is linear in H as one would expect in a paramagnet. M is equal to 0 and H is equal to 0, and a little bit of H, then there will be a small value of M. So the susceptibility and rho 0 to be squared and if you want to put in a 1 over volume, then looking at intensive or extensive, then you put in a volume there, mu b squared and the density of states at the chemical potential. And you remember that in the definition of this density of states, we looked at only one kind of spins. We were looking at only, didn't have a factor of 2. I can put this factor of 2 here, absorb that, and that just becomes then the equal density of states. 1 over volume mu v squared, and the density of states at, now I can put in also, since I'm doing small h, saying that the chemical potential does not change very to first order in H when this H is turned on. So this I can typically put mu 0 here, mu 0 being the Fermi energy, chemical potential when there is no external. So now you see that here, because the fact that the electrons are they form a gas, they are moving, their wave functions are overlapping, etc. So the statistics have to be taken into account. So that when you take into account the Fermi statistics, I get something which is very different. That as you approach t equals 0, susceptibility actually goes to a constant value. Whereas in the other case, when you are just looking at this localized moments, there was the Curie law. So susceptibility was going as 1 over t. But here, just simple calculation, right? I mean, there's nothing very mysterious about it, saying that up electrons and down electrons, they have different energies, and so the way that they will fill the levels is a little different. One goes up to mu plus h, the other goes to mu minus mu v plus h, and as a result, there is a difference between number of up and down electrons, which gives you magnetization, and susceptibility is just what you have calculated over there. So this is important. This is important to keep in mind that when you do even simple calculations, I mean, here again, I am not taking into account any interaction among the electrons, nothing. It's just single electrons, they have spin, and their energies depend on whether the spin quantum number is plus half or minus half. That by itself, with Fermi statistics, gives you the result that susceptibility does not diverge at t equals 0. It just goes to a constant value. And this is verified by experiments. I mean, if you look at metallic systems like simple metals, copper or something like that, you can easily calculate what the susceptibility is. And, of course, I mean, you say that this is a 0 temperature calculation, but even room temperature is like very small temperature for this kind of Fermi systems. Why is that? Fermi energy of a typical metal, do you know? Approximately, roughly, electron volts. How many electron volts? So typically of the order of electron volts, few electron volts. Few electron volts are here is written down. It's 12,000 Kelvin. So even if you're at 200 degrees Kelvin, it is much smaller compared to the Fermi temperature. So basically, even if you do the measurement at in the room temperature, you will see that it's more or less what you get by assuming that the temperature is small. Temperature small is required because, I mean, you are replacing this Fermi function by basically some kind of a step function. And that is true only when cavity is small. But small compared to what? That is what you have to ask. And this is important because it gives you density of states at the Fermi surface. And this is a very important quantity. I mean, whenever we're looking at a metallic material, then many of its properties are determined by what happens very close to the Fermi surface. Because excitations that we are looking at just takes an electron from just below the Fermi surface and put it just above the Fermi surface. That's the kind of low energy excitations that you have. And so there, the properties of these excitations and how many of them you can create, etc., all are determined by the density of states at the Fermi surface. And so, I mean, this is, again, a simple measurement, but it gives useful information about the free electrons, carriers that you have in the system. And not just metallic, I mean, you can also have carriers, a small number. I mean, if you have semiconductor also, you'll have free electrons, conduction electrons, small number of them, etc., etc. So, I mean, this kind of magnetic measurements give a lot of information about those objects. So this is more or less all I had to say about paramagnetism. Just two cases. we have localized spins, then you have Curie law. If you have a special case of that is basically where you have a classical spin, where you have this Langevin function, which also gives you Curie law, and then a bunch of electrons, where taken into account the Fermi statistics and the Fermi distribution, you get a very different result, that the susceptibility remains constant, goes to a constant value at low temperatures, and this is any questions about this at this point? Now I'm going to go away. From paramagnetism, I will spend a little bit of time on diamagnetism. How do you get diamagnetism? Yeah, clear to everybody? How many people have seen this earlier? Sorry.
So I couldn't understand why does that chi not have 2 in the numerator?
Oh, the 2 here. Why the cow? This factor of 2 or
Yeah,
which? Huh?
yeah.
So it is basically so doing the integral from over a very small range. I am assuming that this h goes to 0.
Yeah, but why does the 2 not appear in the chi?
Why does the 2 not appear there? So that's the thing, that there is a rho 0 here and there is a rho here.
Okay.
So rho 0 I had defined as a single particle, single spin density of states. You typically do Fermi statistics, then you would put a factor of sum over k and sigma can have 2 values. So energy doesn't depend on sigma, so we just put a factor of 2 there. Right? So density of states you calculate taking into account both up spins and down spins. But here we are treating up and down spins separately. Right? We are looking at n up and n down. So I'm just looking at single spin density of states. And if I want to connect that to the usual density that one uses, then there is this factor of 2. 2 times rho 0 is equal to rho. Just notation, but when you calculate density typically for electrons, then you take into account both up and down spins when you do the counting.
I just wanted to comment on one thing. What you have is perfectly right. Mott gave a very nice argument for why this is the answer. So he said actually Curie law is always valid, but it depends on the number of free carriers. I mean free moments. The number of free moments is simply proportional to temperature in the Fermi gas because of the rounding.
Oh, I see.
That is proportional to kT.
Uh-huh.
So the number is proportional to kT times rho.
Yeah.
So kT cancels the 1 over kT.
1 over kT. Okay.
It's a nice of Mott.
Yeah, you can think of it like that, because finite temperatures there will always be rounding, and then you look at the little tail. Yeah. But also another exercise that you may want to do is this. Here I am assuming low temperature, where the quantum mechanics becomes important. But if you now go to high temperature, temperatures which are high compared to the Fermi energy, then you should get back a classical result. Here, I mean this, from here itself, I mean there is nothing wrong with it. This we can use at any temperature. At low temperatures, I am assuming that this function, it looks like a some step function. But for high temperatures, it will not be like that. And you can do the calculation at high temperatures. And you will get the Curie law, because there it doesn't matter.
Why is it that when we were talking about localized movements, we assumed the like Maxwell-Boltzmann statistics, but like there also we should have considered those kind Fermi statistics, right?
No, so that's something that I just mentioned at the beginning, that for localized things, whether there is Fermi or boson, it doesn't matter. I don't know whether they are boson or Fermi. I mean, it depends on what S is. I mean, S can be 2 or S can be 1. Then it should be bosonic. I mean, if it is 5 halves, then it will be fermionic as such. So but it doesn't matter.
So are you saying that if I do the calculation there, assuming Fermi statistics, I should get the same result?
No, assuming Fermi statistics means that we are trying to say that the two of them cannot be in the same state and things like that. But that doesn't apply here because they are distinct objects. One is localized here and one is localized there. They are not identical particles.
Okay, I see.
Yeah, maybe it has to do with the comment made earlier, I think by Chandan, that or maybe I missed that you have to have overlap somewhere or the other in the problem.
Overlap is crucial.
If I have highly delta function,
the difference came in from that integral where you have overlap between the two wave functions. So if there are two localized at distinct places, no overlap, then it doesn't matter. Yes.
For the valence electrons, you would assume Maxwellian statistics, and for the conduction electrons, you would assume the Fermi statistics.
No? Why? Because two valence electrons, there will be still, the possibility of overlap.
Yeah, right.
Yeah.
Okay.
Okay. Anything else? So I have about it's getting late. Another half an hour. Okay. So let me just then we'll not go into too many details, but talk about diamagnetism. And there will be something that Musansi was talking about today, this Bode-Van Leeuwen theorem, etc. And some sort of puzzles associated with it becomes important. So here we are talking about conduction electrons, treating them as free electrons. Now the question is, this free electron system, there will be always this. This term will always be there, coming from the spins. But they also have orbital motion. So, if you have a classical particle and you have a magnetic field, then the motion in the perpendicular plane actually are orbits, right? Orbits will have charged particle orbits, and the orbits will have a magnetic moment. So, why there is not susceptibility should not be there, right? So, formally one can show, as he was showing, that you will go from P minus E. So, you have this. I can erase this now, everything. The topic is known as Landau diamagnetism. So, in spite of what she said, which is certainly true for a classical system, but electrons are not not to be treated as classical systems always. So there, actually, magnetic field matters. If we had a free electron gas, apply a magnetic field, then actually we'll get diamagnetic response. Apart from this response coming from the spins response is always paramagnetic. But the orbital part of the motion, that does have some response, and that response is diamagnetic. And that was first shown by Landau. Calculation is not trivial. So let me just point out a few things regarding that. So first of all, there is a puzzle that bothered when you first look at this kind of things. So let's just look at a situation where you have a circular, two-dimensional circular sample, and there are electrons, free electrons in it. But electrons cannot go outside. So there is some kind of a reflecting boundary condition on this circle. So whenever electron impinges, it gets reflected. That's just for containment. The point is now, some electrons are there, and then there is a magnetic field, which is normal to this plane. So I'm doing classical physics at this point, not quantum mechanics. So what kind of a motion of the electrons do you expect? They will have circular motion, right? Circular cyclotron orbits, these are called. So there will be, I don't know, I mean, you have to figure out basically whether it's clockwise or anti-clockwise. Let's just assume that the cyclotron orbit is clockwise. This field, I'm not saying whether it's inside or outside. I mean, you have to use this sort of triangle rule and things like that to find out which direction it will move. But let's say that the cyclotron orbits are like that. These orbits have a magnetic moment. I mean, this is what I began with. Whenever a charged particle moves in an orbit, there is a magnetic moment. So when the field was not there, they were just doing their merry things. I mean, there was no no circular motion of the electrons. They were plane waves, so they're getting plane, not quite plane waves because they're reflecting boundary conditions, but there was no net magnetic behavior. But now we apply the electric field, the magnetic field, and then they go along in circles. And if there are many electrons, each of them will do that, and each of them will produce a magnetic moment. So why do we say that there is no magnetic response? So again, there are, this is a topic that actually, like 20 years ago, the paper, and one of our colleagues, N. Kumar, wrote a paper on this and trying to sort of show that some things that people say are not quite correct and so on. The general folklore is this. Here we are assuming that the orbit is completed, and the orbit is going in the clockwise direction. If you have start from here, and you want to make a, then you go like that. Right? You start a clockwise orbit, which direction the magnetic field is, and it's a defective boundary condition. So it's, and there is a on the in that direction. So I mean, these are very important actually. Even these days, even when people talk about quantum Hall effect and things like that, this is the edge currents that are the important things. So here you have a magnetic moment pointing in one direction coming from this clockwise motion, but the edge one has the skipping orbits. Skipping orbits go in the counterclockwise direction. And so the magnetic moment associated with the skipping orbits, they cancel out the magnetic moment that you get from the orbits which are completed inside the system. You have to do the calculation to find out. I mean, the skipping orbits depends on how far you are drawing this, etc., etc. But one does the calculation, and this is what at least the conventional wisdom is, that although the cyclotron orbits inside the sample, they will give you actually a diamagnetic response. The magnetic moment associated with the cyclotron orbits will be opposite to the, if you just keep track of all the directions, etc., etc. But this will be skipping. So the conclusion is that for classical systems, if you don't do quantum mechanics, then orbital part of the motion of the electrons does not contribute to its magnetic response. There is a magnetic response, which is this Pauli term coming from the spin part of the angular momentum and the spin part of the